And this is a joint work that was done through collaboration between my group at Missouri Science and Technology, Washington University in St. Louis, and Microsoft Research. So the design of SNO, sensor network over white space, was motivated by large and wide area wireless sensor networks. If you look at these applications like urban sensing, environmental monitoring, habitat monitoring, precision agriculture, large civil infrastructure monitoring, large oil field monitoring. Like this figure here, actually, it represents some deployment of like environmental monitoring. As you can see from this figure, this type of applications can be extended over large geographical areas, needing like thousands of sensors connected over long distances. I give you an example, a real example, like Emerson Process Management. They are actually deploying a sensor network that's gonna have more than 10,000 nodes, and that is for monitoring an oil field in Texas. So these are practical examples like where like sensor network applications may need like many thousands of sensors connected over long distances, over large areas. And let's see how today's technology works. 15.4 is pretty well-known technology for wireless sensor networks. We can also use Wi-Fi, Bluetooth, okay? But all these technologies are characterized by short range, very short range, 20, 30 meters, 35 meters like this. So what happens to those applications? They actually become, those deployments, sensor network deployments over large area, they actually become networks like this. It's multi-hub network, which is pretty good. Like it's very, like theoretical people can solve many interesting problems and it works, deployment works, okay? But when you go to the real field, you have to face a lot of engineering challenges. So it works, but we manage it at the expense of energy, cost, and complexity. So it limits our scalability. Let's consider let's see how it happens really in deployment. Okay, so we consider a multi-hub network and consider a pretty large network, okay? And we take a pretty good MAC protocol, which is energy efficient. So Probal just left his Probal's AMAC protocol. And I'm showing that it's not going to work well, so he should not be unhappy. But anyway, so AMAC is considering today's technology, say 15.4 technology. And we also envision some network where we can reduce the number of hubs, say we can make single hub, okay? And single hub actually does not mean always good, because if you just serialize the transmission, that's gonna be bad, like only one node can transmit. So we envision some more smart design. What design you're gonna see? Just consider that many nodes can transmit to the same node or to the same base station at the same time. So envisioning this type of design, we consider like we have a design called SNO, and we have the traditional technology design called AMAC, and we consider converged crust. And you see the latency on the second figure and energy consumption per node on the first figure. Like that new design, that looks great. But network performance, both like latency and energy consumptions are pretty good. So obviously I have to grab a solution like this. Then the question is, can we really do that? So we can answer this question here. Actually, we can do that. So today there are many other technologies, like many of you may have already heard this NB IoT, 5G, Sigfox, LoRaWAN. These are some technologies, actually they are not very old. They are actually, we should say, they are developed in parallel with our work. It's not very old, okay? And NB IoT, 5G, all these like technologies here are actually they are low power and for wide area networking. And NB IoT and 5G, they actually depend on existing cellular networks, so you have to subscribe. So you operate on licensed bands, so forget about those. Sigfox and LoRa, they operate on free bands, so this is pretty good, affordable. But both of these technologies consider a very low traffic to achieve scalability. And Sigfox has like message size like 12 byte, and every device can send at most 140 messages in a day. And both of these classes, like Sigfox and LoRaWAN, they have very low duty cycle. A device has to duty cycle 0.1% or 1% based on what subband they use. So LoRa does some better things because LoRa actually, a gateway uses 8 radios, which means like it can actually afford 8 simultaneous or parallel transmissions or receptions. Okay, so the conclusion here is both of these technologies achieve scalability in terms of number of nodes, assuming only very, very low traffic. We're gonna beat them actually. We do much better. And that's how you design sensor network over white space. So what is white space? White space is the free television spectrum, which means the TV band that is allocated for television broadcasters, but not locally used. As typically those bands are for United States, these are in this range, between 54 and 698 megahertz. And in 2009 in United States, actually the FCC gave the permission to use the free TV bands as unlicensed users. And the similar rules are being adopted across the world in many countries. And the thing here is the condition here is that you cannot interfere the primary users. Primary users, the TV broadcasters or wireless microphone users. So don't interfere, that's illegal. Don't interfere those users. As long as you don't interfere those users, you're fine to use it. Okay, so the advantage here is like, there are low frequency, right? So that's why like, they can actually easily penetrate walls, goes like too far, okay? So pretty long communication range. So we should grab it. And other advantages is pretty much available. It's not like ISM band, which is crowded everywhere. It's overly crowded, ISM bands now. So these are free resources. See, this is data across United States, and on x-axis we have the channels, TV channels, and y-axis shows the number of counties. There are approximately 3,000 counties in United States. Number of counties where this particular channel is available. So this figure shows that a lot of number of channels are available in a lot of places. Free resource. Why don't you grab those? People are actually already grabbing those, like industry giants like Google, Microsoft, they're already using it. Even research community, they are exploring it. Standard bodies, they're modifying their standards, okay, to exploit white space. But most of those cases, most of the scenarios or applications that they are considering are for broadband access. So we make a turn there. We want to exploit this for sensor network because we don't want to stay in ISM band always. So, but it's not easy. You cannot just grab the resource and start using it, okay? We have to look for the demands and requirements for sensor network. So what are those? Sensor networks are pretty poor devices, right? Those are very energy efficient. Have to be energy efficient, they're power constrained. But TV broadcasters, they are pretty rich, right? They have like a lot of energy, but how can they afford to operate on those bands and achieve long communication range? It's a challenge. And also we have to achieve the scalability. And long range sounds pretty good. We can remove like multi-hub network, reduce multi-hub network, make it a single hub network, but that's not just the advance in one sense, but it can create a lot of problems because when your communication range is pretty long, that means you're interfering many of your friends. And you are gonna be interfered by many guys. So, and at the same time, you have to be energy efficient. So we have to handle this very, very carefully. Let's see how we do this. So first, see our architecture. As I said, it's a long range, and it's long means it's like several kilometers. It can be 4, 5, 6, even 10, 20 kilometers. Okay? So forget about multi-hop, come to single hop, okay? So all nodes can transmit to the base station just directly, okay? There is no through node. And vice versa, base station can also send to the nodes directly using single hop. And The base station is considered line powered, so don't consider the power constraints at the base station. Okay, which is like pretty like realistic assumption. And it's also connected to the internet. We consider it has to be connected to the internet because to learn about the white spaces in your area, okay, because you have to consider your location and availability of white space varies based on the location. So you have to give your location to a cloud where there is a database. The database actually contains which channels are available at which places. There is another approach which is called spectrum sense, and you can have one extra radio continuously sense which channels are available here. But we don't go to that approach, we just follow database approach. So that's why we consider the base station is is internet connected, so it can access the database. And white space, as I said, it's available in many places, especially go to the rural and suburb areas, you're gonna get huge white space spectrum. I came from town, Rolla actually, it has most of the TV channels are free there. I know, which means you're gonna get huge spectrum, okay? So base station is gonna grab those. And if you grab the whole spectrum, but your sensor nodes are pretty tiny devices, how can they exploit that huge spectrum? That's a big overburden for them, right? So what you do is split the channels. Let's make pretty narrow channels. And the base station gives those narrow channels to those poor devices. So the devices remain power constrained. Okay, the sensor nodes or devices, the sensor devices remain power constrained. So they don't have to do any spectrum sensing, they don't have to do any cloud access. Okay, the base station actually accesses on behalf of those and assigned to those nodes. So every node operates on a very narrow channel. Just consider this is my base station here. It's connected to the internet and these are the tiny nodes, okay? Every node has pretty small narrow band. Narrow band is good. Narrow means like it consumes less energy and it can also go too far. If we just go back to the Friese equation of transmission. Okay, so what is our goal? Now we have seen we have pretty huge spectrum, and the whole network is now single hop. And if you consider single hop network, and just you depend on traditional wireless communication that only one node is gonna transmit to the receiver, then there's no use. You cannot exploit that huge spectrum. Then how can I do that? We should make some change here, a significant change here from the traditional technology. We want this. So many nodes, a lot of nodes can transmit at the same time to the same node. It's not like conflict resolution, okay? Without any interference, many nodes should be able to transmit to the base stations, okay? Without that, there is no use of having like huge spectrum. Even if you have infinite spectrum, there is no use if it's just one node can transmit at the same time, okay? So that's our key goal. So we want to go some steps further also. We also want to adopt that nodes should be able to transmit whenever they want. Okay, so just allow asynchronous transmissions from the nodes. How do we do that? The key in our design is distributed OFDM-based physical layer. So we handle most of the challenges at the physical layer. And we design the physical layer based on distributed OFDM. OFDM, you already know, is the orthogonal frequency division multiplexing. If you have this spectrum, you split the spectrum into subcarriers, okay? And typically, you need to maintain the gap, the guard band between the spectrum. But when you make orthogonal, they can actually overlap. As you can see, then you can actually make many subcarriers. So here, we don't adopt the traditional OFDM. DFDM is a distributed implementation of OFDM, okay? So, the nodes, the sensor nodes transmit on narrow OFDM subcarriers, which means it's energy efficient and also there's a spectrum efficiency that gives scalability. And as I said, narrow subcarrier means the narrower the channel, the less energy will it need. And here we just consider very simple modulation, but it's not restricted only to ASK. We implemented used based on ASK. So every individual subcarrier is modulated based on ASK. And nodes asynchronously transmit to the base station, okay? That's why like we can have simultaneous reception at the base station. that gives scalability. So we get our goals. So how do we realize DOFDM in our design? The distributed orthogonal signals are generated by the distributed nodes. So everybody independently encodes its data, okay? So then the transmit on the air, that signal can be represented just like this. There's the time domain representation of the signal. And when the signals come at the base station, you can represent the signal actually looks like this. So the base station now should decode this composite signal, which is very, very challenging. You know, the key challenge here is that, which typically like WebDM transmission needs, it needs a strong synchronization. When you consider between just two nodes, one transmitter and sender, that strong synchronization between the subcarriers is okay, you can handle it. But in DOFDM, the distributed nodes have to be strongly synchronized, which is impractical. It's very difficult. It's not like typical synchronization that we consider. It has to be just like, almost like ideal synchronization. It's very challenging. So we tackle this considering that give the load, the entire complexity or most of the complexity to the base station. And leave those poor guys very simple. Don't give burden on those sensor nodes. That's the trick here. So what do we do? First, we keep the base station always on. That sounds bad, but it's not actually unrealistic. It's pretty good. It's line powered and we don't care if it's always on, okay? We just keep the base station always on, which means it can receive asynchronous transmissions, okay? Whenever you guys transmit, base station is ready to welcome. And then to extract, but what does the base station receive? It receives composite signals. So it's not easy to decode, to retrieve that data from individual subcarriers, to single out the subcarriers, okay? So to extract the spectral components from the composite OFDM signal, we adopt fast Fourier transformation. But we don't just take it as it is, we adopt the fast Fourier transformation as a global FFT, which means the base station operates on the entire spectrum and we don't run FFT on each individual subcarrier. We run FFT on the entire spectrum of the base station. That's why we call it global FFT. So we run FFT on the entire spectrum, and then from the FFT outputs, we consider frequency bins, and from the frequency bins, based on the modulation technique that we use, we retrieve the bits from every subcarrier. Which means if some nodes do not transmit, it still works. Only the subcarriers that are carrying data, we can retrieve the data from those subcarriers. So this is what happens at the demodulator or decoder at the receiver. So it samples the carrier signals, then this carrier signal, these samples are actually fed into a serial to parallel converter that gives the output to the GFFT algorithm. GFFT gives the output like this, okay, on every subcarrier. So we are gonna get the beats here, so you have to pick the beats here. What do we do here? Because the nodes can transmit at any time, okay, so it's not synchronized. The transmissions are not synchronized. So we just maintain a 2D matrix here, okay, where the matrix will look like this, okay? So your data bits are like, if you consider one column here, it's gonna represent one packet, okay? So, and if we just, the time, it also represents the time, okay? So it's changing in terms of time in y direction. So here, the bit ij indicates the ith bit on the zth subcarrier, okay? And you can, using the preambles, using the packet end marker, you can detect when a reception is complete, okay? So this approach also allows us to exploit fragmented white space spectrum, which means white space can be actually largely fragmented, okay? Because you never know, like which TV channels are using what channels, okay? It's pretty much fragmented. So which means you get some channels free, then the next channel is not free, then again some channels free, okay? It's called fragmented spectrum, and we can actually exploit it, especially when you need huge scalability. We can take the entire spectrum that we find here, okay, and use it because of this approach that we are adopting. Okay, so this is our physical layer design. So we have to, as I said, we handle most of the complexity as the physical layer. So on the upper layers, we have actually less burden. So we can keep the MAC protocol very simple. So what is happening at the MAC? Especially this is needed when you have the number of subcarriers smaller than the number of nodes. Especially when you have the number of nodes less equals the number of subcarriers, there is no problem. Physical layer is done. We don't need this type of MAC layer, okay? Because every node can have unique subcarrier and they can transmit, they can enjoy that subcarrier always, anytime, anywhere they want. But just consider you have many nodes and you have limited number of subcarriers. So we consider that the base station gets the entire spectrum and it splits into the subchannels or subcarriers. Just consider you have n subcarriers per communication. We also consider some stable subcarriers which are relatively stable for download communication, for management purpose or control purposes. Okay? So when the number of nodes is larger than the number of subcarriers, nodes are grouped. Okay, so every group can have like n nodes, okay? So in a group, every node can have a distinct subcarrier. So our communication happens in phases. We can consider upward phase means the nodes are gonna send to the base station, and then you're gonna have downward phase. The base station is gonna transmit control messages or management messages to the nodes. So in upward communication, we can just like schedule the groups in turn. First, we select one group that the nodes in that group can transmit asynchronously within a time interval, okay? Then, the next group is selected in round robin, and if a node doesn't have anything to transmit, it can sleep, it can duty cycle, okay? Also, if it's not the turn of its group, then it can also duty cycle and sleep. It can sleep. And this repeats always, okay? So next happens the downward communication after an upward phase. For downward communication, we have some reserved channel, management channel, as I said, like we take some more stable subcarriers for management communication. So all the nodes, including the base station, they switch to that management subcarrier, one particular management subcarrier or control channel, FC, okay? Then if the base station has any message, anything to send, then it broadcasts to those nodes. And obviously all these nodes in this mode, downward modes, the nodes are in receive mode. And this happens continuously, it repeats forever. So we have to do some dynamics handling. One key dynamics in white space is called spectrum dynamics, because the availability of spectrum can change if some radio stations operate in different times, different day, okay? When they don't operate, you are allowed to use it. Also, if some people start using wireless microphone, okay, you should like back at that channel. So this type of dynamics, also considering noise conditions on the channels. So when availability of spectrum changes, the base station has to reallocate the subcarriers, okay? Then it can be done actually in the downward phase. Then some other kind of dynamics like node addition, node joining, okay? So nodes can actually join in the upward phase because we have some reserved subcarriers for management. So some new node can actually transmit their message on those subcarriers and the base stations can know it. Another key thing in this design is called reliability, which is very, very important for wireless communication. But here you see, we cannot adopt per packet acknowledgement because our system is asynchronous, okay? So if we have just single radio at the base station, it's receiving always an asynchronous, it's very difficult to adopt per packet acknowledgement. So we cannot do it, okay? But it's not impossible, it's not infeasible. We are working on this. But currently, what do we do? For reliability, we have to adopt some sort of reliability. So instead of per packet acknowledgement, what do we do? A node can proactively send the same transmission multiple times, okay? And also we adopt some forward error correction through bit spreading. That also helps a lot and gives reliability. So that's our design. So we implemented this in GNU radio with to use the USRP devices. That's the software radio peripheral devices, universal. Okay, so we implemented this and we tested. We had only 6 sets of devices. So we experimented with 6 devices. And for larger scale, we did in the QualNet simulator. And good news here is that this is for one scenario when base station uses 6 megahertz spectrum. 6 megahertz means a TV channel. A TV channel is 6 megahertz, okay? Then using 400 kilohertz, we can get 29 orthogonal subcarriers or orthogonal subchannels. And if 29 nodes transmit at the same time, the base station can decode all 29 packets within 0.1 millisecond, which is just comparable to a single packet decoding time. That gives the scalability of this design. Then we have the design parameters. These are the key design parameters, like bit rate, we target like 50 kbps is enough for us. Packet size, we test with various like packet sizes, and it works pretty fine. Although we set like most of the tests were done using 40 bytes, which is pretty reasonable size for sensor network. Then subcarrier bandwidth, beta spreading factor, all these are determined both theoretically and experimentally. So first we do the calculation and get these values using Shannon-Hartley theorem and Shannon capacity theorem. And also then we determine based on the experiment. Okay, and our default settings here, as I said, we have only a small number of nodes, so we consider a pretty small band. We mostly operate in this band, that was white space in the area we experimented. Transmission power default is set at 0 dBm, subcarrier bandwidth default, although we tested various like subcarrier sizes, but this was a default value 400 megahertz. Sorry, it should be kilohertz. Typo. Bandwidth was 6 megahertz. And packet size, default size was 40 bytes. Beta spreading factor was 8. And our distance in the indoor buildings were like default distance was 100 meters between the sender and receiver. And outside it was 1.5 kilometer. So this is one say like location where we did some external outside experiment, outdoor experiment. And this figure is showing the performance using different subcarrier bandwidth. Okay, so we started testing with 200 kilohertz to 100 megahertz. And y-axis shows the correctly decoding rate, which means what's the percentage of packets that we can correctly receive or correctly decode. And as you can see, all subcarrier bandwidth is pretty okay. And over distances, although we went up to 1.5 kilometers because we often got stopped by like law enforcement forces, so this is in our safety zone. That does not mean that we can go only up to 1.5 kilometer, okay? It can go even much further. So here we select only 400 kilohertz because that also gives us bit rate 50 kbps, so that's our default setting. Then considering transmission power, we vary transmission power, tested minus 20 dBm to 0 dBm, and at 0 dBm, as you can see, we can go up to 1.5 kilometer, not up to 1.5 kilometer. We tested up to 1.5 kilometer, and 0 dBm is actually pretty fine. And we did not test any further. And then subcarrier overlap, we use 2 subcarriers that are overlapping, and those guys are transmitting to one node. See what happens. Subcarrier bandwidth default was 400 kilohertz. So when they overlap by 200 kilohertz, which means that if there is 50% overlap between 2 subcarriers, they are actually still pretty good. We have close to like 95-96% packet reception, packet decoding rate, correctly decoding, which means subcarriers can overlap up to 50%. Our indoor setup was like this. This is the computer science building, Missouri Science and Technology. We had 6 nodes. They were placed in these locations, showing on the floor plan of the building. So maximum achievable throughput we are showing here using different subcarrier sizes and number of subcarriers, different bandwidths and number of subcarriers on x-axis. Y-axis shows the maximum throughput, achievable throughput. As you can see, our maximum achievable throughput linearly increases as we increase the number of subcarriers. Because we can actually afford those, no matter how many subcarriers are sending, as long as the number of senders is less than the number of, or less equals the number of nodes, like we can actually decode at the same time, within same time. That's why it actually gives so good performance. So with this, I'm done. So we have designed sensor network, which is a sensor network design over TV white spaces. And these are mostly for large and wide area wireless sensor network applications. Sonar actually holds enormous potential for future Internet of Things and cyber physical systems. And it can also help shape and evolve the standards like IEEE 802.15.4m. That's a new standard coming, and its purpose is to exploit white space for sensor network like applications. Our design gives great results. It achieves scalability, energy efficiency by achieving these other things like making multi-hub network a single hub network. Using overlapping orthogonal subcarriers, we can create many subcarriers. We can afford many nodes. And narrow subcarriers, which needs actually less energy. Then simultaneous receptions, asynchronous transmissions, all these things give pretty good scalability. And our future work, we want to design robust SNO, where we want to adopt more robust modulation techniques like OQPSK, BPSK. We also want to make it more efficient in handling dynamics. Then another thing, as I said already, we want to enable per packet acknowledgement and two-way communication, which is very, very difficult, but I know that it's not impossible. So that's why we are still working on it, and it's a good future work for us. Thank you.
Questions?
Hi, Usman Raza from Toshiba Research. So basically, good work, thank you very much. Weightless W is one of the standards that was first white spaces standard designed by Weightless special interest group. And they have not been pushing it for, and they moved to narrowband and other kind of standards. So why do you think, I mean, after there was already a weightless W standards, then why you should propose a SNO standard? How the SNO standard is better than that, and what are the design goals different than, let's say, weightless W standard?
Yeah, good question, actually. I also know about weightless standard. Later, I was actually following their progress, but I think at some time they stopped it, right? I don't know if they switched to some different, work, or I don't know, but that is stopped, I think, okay? So here, the standards actually, I have not seen any standard like, say, 15.4m, that they're considering that a node will receive from many nodes at the same time, okay? No standard is talking about that. That's our key goal here for achieving this, okay? That should be the fundamental difference between these and those works.
Okay, that brings me to another question. How many subcarriers you can demodulate at the same time? That's, I don't think you have mentioned in the slides. Maybe you have to read the paper that you have.
Yeah, so for experimental experience, I can tell you, because we have limited number of devices, okay? So the real experiment was like, we considered base station was operating on 6 megahertz channel. That's just like a TV channel. And using 400 kilohertz subcarrier bandwidth, we can afford, and with 50% overlap, we could afford 29 subcarriers. Okay, if 29 nodes transmit at the same time, okay, then we can decode within 0.1 millisecond. That's the real experience. That actually gives some sense that how scalable it can be.
Okay. And my last question is basically the end devices are very sleepy devices. So their design goal is that you want to save as much energy as you can. So basically in those sleepy devices, the downlink coordination that you do from the base station to the end devices to do time synchronization or when they should communicate, how do you design it, and what are the energy trade-offs there, and how you are actually solving those energy trade-offs?
That's another very interesting question, actually. Yeah, it's actually time synchronization, but it's not like that type of strict synchronization. It's very loose synchronization that you get as a byproduct of the communication. So which means the nodes can actually send the beacons, periodic beacons, and you can actually tell the nodes, this is my period, okay? And based on that period, actually node can wake up, okay? And if a node doesn't have any data to transmit, it can actually sleep, okay? And if, okay, so in this we're actually doing some duty cycling, okay?
Pony from Stanford, very interesting work. Can you give some comments about why the Sigfox only supports 100 bits per second data rate? Is it because of the difference between the Sigfox physical layer or between your solution, or is it because of the Sigfox target at supporting 10,000 devices, something like that?
Okay, for Sigfox, the first thing is Sigfox still does not have anything open for public. There is no specification, there is no standard. This is only from the information that I got from some other documents who have access to Sigfox. First of all, if you mention the bit rate, I think I don't I'm not pretty much aware of their beater, but what I know, they have, this is their design. The device is required to follow that, okay? The message says at most 12 byte, and every device is allowed to transmit at most 100, how many, 140 messages. That is the requirement. Requirement is why I don't know. Maybe the applications that they consider, the application, those are good for those applications, okay?
I understand the protocol part of, I'm thinking about if the Sigfox use of physical layer design, will they significantly improve their data rate, or?
Your question is whether, sorry.
If the Sigfox use the OFDM design that you propose on the physical layer, right, will Sigfox significantly improve their data rate?
Obviously, I think so. I think so. But we don't have access to their physical layer, as I said. But I think so, yeah. And many technologies can actually exploit that.
Okay, thank you.
You're welcome.
Hi, I'm Advait Dongre from Carnegie Mellon. Great talk. So I'm curious, like when others start using the same white spaces for their own communication, how does Snow scale with those? Like if there are multiple users over white spaces, because then you can't just depend on your database to figure out if the channel is free or not.
So multiple users, you mean what? Like if we can support already many users, okay? We had some analytical calculation that actually shows, I don't have the result here, that shows that even if you compare with the LoRaWAN and those things, okay, we have many times better scalability. So we already handle multiple users.
What I mean by multiple users is users who are not registered in your system. So it's like, say, an independent group who are running their own experiment.
I got your question. Okay, so that is something like we're considering, we consider interference from other sources, other users. That's good. This was, as I said, in this line, this was our first work. So this work was considered only just considering you are the standard user. Okay? But we are actually working on that, considering other people are also using a spectrum, then how should you handle, how should you design your MAC protocol? This is some work in progress in our group.
Right.
Thank you.
Thanks.
Thank you. Any more questions? Okay, let us thank the speaker again.
Thank you.